Right. Well, first of all, I think I'm going live. I'm not sure if it's um out there. Am I going live right now? I'm not sure. How do I do? I'm sorry, I'm just trying to figure this out. Um, okay, so here it is. Okay, so now I guess I have to. How do I figure this? Okay. Not sure. How do you share the? Oh, okay. I think I know. Is it like this? Oops. Something like this. Yeah. But I'm just seeing the entire thing. Okay. Can you hear me? Please tell me if you can hear me because I have no idea if you can see me. Because I've never done this before. Yeah. Let me see. Yeah, I think you can hear me. So I'll probably just wait for a bit. Hi, I think I probably should start now, right? Right. Please say you can hear me clearly if you're here now, because I'm not sure how it works. I'm so sorry. Never done this before. Let's see. Okay, should I start now? I guess I should start now. Right. Yeah. Thank you for joining me here. So whatever, if there is like problem when you can't hear me, you can't see me, please do let me know and at the comment section, because I've never done this kind of webinar before. So just bear with me as I'm trying to figure out everything. And so yeah, today I'm going to be talking about my work and remote sensing and environmental monitoring. So my name is Florina. I'm currently doing my master's at Swinburne, and I'm also a graduate research assistant with the Sarawak Multimedia Authority and also Swinburne University. So, so what happened? A bit about myself. So that's me. So, like I said, I'm currently doing my master's with Swinburne, and also a GRA for SMA. And last year in fall, I was in the United States doing my fellowship in the University of Montana in global environmental issues. And then at the end of last year, after I got back, I started my own project called Plastic and Society, where I got a grant from YSILI. And a few years ago, I was also in Arizona in USA, where I was a part of ISAF, where I was a student scientist, and now I'm an alumni. So let's get to my my sharing for today. But if you have any question, you can just drop in the comment section below. So today, my sharing is going to be divided into 3 different parts. The first one is basically the mechanism of remote sensing and like how does it work, and just on the surface of it. And then the second part of it, it's going to be focusing on my model and the thing that I'm working with the Sarawak Multimedia Authority. And the last part, I will be talking about the conclusion. I'm just going to wrap up everything, and then I am going to be basically just going to wrap up everything. So let's jump right in. So the first thing is remote sensing. So for those of you who are not aware of what remote sensing is, actually remote sensing is something that is very close to us, something that we use every day. And the closest example to us is actually our eyes. So our eyes are actually looking into, for example, you are looking at the screen right now, but then your eyeballs are not having in contact with the screen at the moment. But then your eyes are capable of obtaining that information for your brain to process. So that is the basic idea of remote sensing. So by definition, remote sensing is the science of obtaining information from an object or a phenomenon without having any physical contact with it. So in the area of remote sensing research, there are a lot of remote sensing instruments available, and that includes drones. Also, there are sensors attached to airplanes and sensors attached to hot air balloons. But the one that I'll be focusing on here today is called the satellite remote sensing. I'll be focusing on this because this is the one that I am currently working with. So here it is, up in the space. So next, let's go back in time. So how did all of this remote sensing started, and how did it came about? So actually it started in the 19th century, whereby balloonists, they took pictures of what's happening on the ground from up there, from hot air balloon. This was when the photo camera was first invented. So when they took the pictures, and then they were like, oh, this is a nice view on the things that are happening on the ground. They can see a clearer picture. They can see a better picture on what's happening on the ground. So, and they did that a number of times. And then only in the early 20th century, whereby Dr. Newbrenner, he is a physician, he normally used pigeon to exchange prescription and medicine with the sanatorium he was working with. And so one day, one of his pigeon was missing. And so, and it only returned back a few weeks after that. So he was wondering, where did it go? What route did it take? Where did it gone to all of these weeks? So he had this idea of attaching a photo camera to the pigeon, and that camera was able to take pictures at a certain interval. So he had an idea of where it went to. And so, it did. He did that, and he was like, "Oh, this is cool." And so he patented his idea, and he got the patent. So that's how it's evolved from balloons to like using pigeons. And scientists and engineers in the midst of 20th century, in 1957, the Soviet Union launched the very first satellite into space. And that satellite, it's called Sputnik 1. So in comparison with the current satellites that we have in space, Sputnik 1 is a very small satellite that it weighs under 100 kilogram. And then, as you can see from the GIF image here, that it was actually battery powered, silver zinc batteries. So because it was battery powered, it only lasted for about 2 weeks before it died and it spiraled back to the Earth's surface. But you see, the thing is, although this satellite is so small and it only lasted for 2 weeks in space, after more than 60 years, Sputnik 1 is known as the satellite with the highest impact. After all of the satellites that we developed, it is still the one of the well-known satellites. And that's simply because, number one, when it was sent to space, as it spiraled back to the Earth's surface when it died, it was able to tell us the density of the Earth's atmosphere at a different altitude. But the thing is that, and that tells us a lot about the characteristic of the Earth's atmosphere. And other than that, scientists were also able to know radio wave characteristic and other parameters it was also measuring. But the highest impact of all is actually, when scientists and engineers launched these satellites into space, they were able to prove like, hey, see, we launched something to space and it worked. We can launch object and this object can take measurements for us. And they prove a few theories and principles about launching instruments to space for research. And from that time on, countries and organizations that were investing, that were pumping in money to build more and more satellites. So that's why, as of April this year, I'm sorry, we have close to 5,000 satellites in space. I hope you can see the. Can you see the video? So you can see that you launch a lot of this. You can see that there are a lot of satellites in space. Yeah. So with this, I think it's projected on the screen. You see, this is the artist's impression on the amount of satellites we have as of this year. But out of all of these satellites, less than half of the satellites actually function. So more than half are actually dysfunction. And all of these dysfunction satellites, they are known as space debris. And it wasn't engineered to return back to the Earth's surface. That's why it stays in the Earth, in the space. And and scientists realize that this is actually a problem because we have more and more stuff in space, and space debris could really be a serious problem to outgoing spacecraft because like collision and stuff like that, it will really affect the things that are happening in space. So like only recently, scientists they designed a satellite that has enclosed inverted coma parachute that once the surface ends, it will spiral back. It will travel back to the Earth. And so out of this close to 5,000 satellites, they're actually divided into a few purposes. So one of the most common one is the communication satellite. Like for example, like this webinar is made possible through this communication satellite because internet and all phone calls, these are all it's using communication satellite. Another one is weather monitoring satellite for your weather forecasting. And the next one is the environmental monitoring satellite. It's the one that we'll be going to focus on now. And for like super private and confidential communication, so the military, they launch military satellites. So it's for military communication. And there are many other kinds of satellites out there, but these are the ones that are very prominent. Now, next, so the types of satellite, the history of satellite. So have you ever wondered how our satellites go up in the space? How does it work? How does it function. So there are two major parts, how it operates. Number one is the geostationary satellite, and which is represented by the green color one. Another one is the polar orbiting satellite, which is the yellow one. So let's go into the geostationary satellite. So geostationary satellite, it's not literally stationary. It just does not stay at the same area in space. So what it does is, why it's called geostationary satellite is, geostationary satellite, it travels at the same velocity as the Earth. So I want you to imagine this. So as the Earth spins at its orbit, the geostationary satellites, it also travels at the same velocity. So that means if you launch a satellite to, for example, Malaysian space, it will stay there because it moves as Malaysia moves. If that makes sense to you. So because it stays in the same space area all the time, so geostationary satellite, it's mainly for communication satellites. So if a communication satellite belongs to Malaysian government, it's mainly for communication within Malaysia. And the next one, it's called the polar orbiting satellite, which is the one in yellow color. So this polar orbiting satellite, they move from pole to pole, means north to south, south to north. And as it moves up and down on the Earth, taking measurement of the Earth's surface. So, and at the same time, the Earth, it spins at its own velocity. So in that way, it can take measurement of more area on the ground. So you see, it's taking like up and down kind of motion, and then the Earth is spinning. So it covers more area compared to the geostationary satellite. So this is the kind of satellite, because it can cover and can in close inverted comma again, see the Earth, can see the Earth at a more like bigger area. So this satellite is applied in the for environmental monitoring. So this is like the most of it, not all, but most of it applies this kind of mechanism and how it operates in space. So next, when you look closely into a satellite, these are the major parts of the satellite. So the satellite, so these are like the main parts. So satellites consist of antennas. So basically, this is like for communication between the satellite itself and also the ground control center. So if you have watched all of this space movie like The Martian and all that, they have this control center like NASA, right? So yeah, basically this control center, it communicates with the satellite by using this antenna. And the next one is the solar panel. So you see, in comparison to Sputnik 1, which only lasted for about 2 weeks in space, the current satellites, it can last up to probably about 15 years. And that's because it's not battery powered. The main source of energy is the sunlight, and it's because of this solar panel. But in case it's not exposed to sunlight, it will be battery operated. So that battery is inside the satellite itself here. So the satellite, but then the batteries that they are currently using in our satellites, our current satellites, are like the more advanced ones, not like the one in Sputnik 1. It can last to also support the lifetime of the satellites for like 15 years. And then next thing is they have fuel tank, and that fuel tank, fuel inside the fuel tank, it helps to power the rocket motor. And bear in mind that the rocket motor, it's not to keep the satellites running. It's not to keep the satellites going around the Earth all the time. So what the rocket motor does together with the fuel is, so in case a satellite moves slightly away from the orbit, so the route it should take, so the people in the control center on Earth will send a command so that the satellite will move back to its orbit. So that motor actually does that job. And of course, there are onboard processes. It's just to process everything that is going on in the satellites. So, however, so this is a basic parts of a satellite. But for environmental monitoring satellite, they have sensors attached to it. For example, this one. The sensors are extreme ultraviolet and X-ray irradiance sensors. So the sensors can be like different kinds of sensors. So basically, it can take measurements depending on why you launch this satellite. So the sensors will be designed in such a way to measure the kind of thing you wish to measure. And so you know now the technical part of it. Now let's look into more chemistry part of it, but this is just on the surface. So like I said at the beginning of my presentation today, so I said that our eyes is the closest remote sensing instrument to us. And our eyes can only see the visible region in the electromagnetic spectrum. So that's why we can see what we see today. We can see this much only. But what makes a satellite so powerful is that the satellite that has sensors that are capable of seeing the invisible beyond what we can see. So, for example, now as our eyes are open, we can see the fact that something is white, something's green, something is yellow, and that's about it. But can you see the air? No, you can't. But then remote sensing can see what is in our air, the gases that are in our air. It's beyond, like I said, it's beyond like what we can see. And so not only that it can see, it can also give out numbers here. So for example, when you see plant A and plant B, right? And you can say, oh, plant A, it has lighter color than plant B, and plant B, it's darker color. You compare in such a way, but that's about it. That is about our human capacity. We can only qualitatively say something, how dark is the green, how light is the green. But then with remote sensing, it can give us out numbers. It can give us out a value to how dark is the green, how light is the green. So with these numbers, it gives us power, and it gives us data. We are able to use these numbers, and that we fit that numbers into formula. And depending on what you want to calculate, depending on what you want to measure. So from this remote sensing data that gives us numbers, feed it into formula. And then this formula can give us information. And that information, you are able to visualize that information. So yes, that's how powerful it is. Great. Yes, next one. How can I see? Sorry. Do you guys have any questions? Just checking the comment section. Sorry. I think it's quite slow though. I mean the video and I mean the slides and also my voice, right? And yeah, so you can visualize everything. So the next part is I'm going to be talking in specific to the thing that I am working with in Sarawak. So maybe you're not aware of where Sarawak is. So this is the map of, you can see Malaysia there. Here is Malaysia. Oh, can you see the map? I'm not sure if you can see the map. Is the map up? Okay, I think there's a problem. Wait, how do I see this? So, yes. Yeah, okay, can you see the map now? Because I think that there's like, my voice and the map is delayed, I think. I'm not sure how it works. But okay, anyway, let me just continue. So this is Sarawak. This is where I live right now. So Sarawak, it's the biggest state in Malaysia, and it shares border with Kalimantan, Indonesia. And yeah, but there are two things you need to know about Sarawak. Number one, agriculture is the something that drives its economy, that drives its economy, and it's one of the major activity in the state. And the next thing about Sarawak is that the area is so massive and that we also still have a lot of remote areas. And why do I say this? And these are the two things, the 2 points where you have to bear in mind as I go to further into my work. So the reason why the Sarawak state government, through this agency called the Sarawak Multimedia Authority, is because they know that agriculture drives the economy, and also it has a lot of remote areas. They thought, oh, we need to figure out something to help us monitor and help us understand what is happening in the state. So that's how they gave us the grant to build that models by using satellite data, by using remote sensing, to access the areas that are unreachable. So if you want to understand what's happening in a very, very remote area, in a very, very far area, they want us to understand what's happening there, but you don't have to travel to that place. You just have to use satellite data to help us understand what's happening. Now, the next thing is Swinburne. The next stakeholder is Swinburne. So Swinburne is where I'm currently doing my master's. So there are two campuses. One is in Australia, another one is in Malaysia. I'm currently based in Swinburne in Malaysia. And the next one is the European Space Agency. So the European Space Agency help to fund our data acquisition. So to get the satellite data, you need money, but it costs us a lot. So that's how ESA help us to pay for that data acquisition. And yeah, that's the team. So I'm currently working with Dr. Moritz Muller, Associate Professor Moritz Muller. So he's the principal investigator, and that's Jack, and that's also me. Okay, can you see I just want to check, is the audio and the slides tallied, or no? Is it tallied, or is it the same, or is it slow? One is slower than the other? Okay, just let me know if it's, something's not right. Because it seems like one is fast, my voice is faster, and the slide is slower. But anyway, it's just continue. So yes, so that's me, that's Jack in the middle, and that's Professor Moritz. So we work together as a team to build that model. And on your right, I suppose, that's me doing the ground field data acquisition. So yes, how do we build that model? So you have an idea that we use satellite data. Now, in what way do we build it? So the main system that we use to build our data is this called the Google Earth Engine. So the Google Earth Engine, it's a cloud computing system that helps us to analyze the satellite imagery data. So if you see at the bottom here, there is this, it says satellite imagery. I hope it's clear. And the next one is you add your algorithm to it. And then you can now, by combining your satellite imagery and the algorithm, you can have a real world application. Means it can tell you what it's looking at. Say in my study, I'm focusing on 3 different parts. I'm looking into plant health, biomass, and also yield estimation. So these 3 things. So these 3 things that I'm focusing on in my study. So when you you click into the main area, working area for the Google Earth Engine, you can see this system. So in the area up here, you can see the script where you write your script, when you write your code, and here is where you will add the numbers and values. You interact with the satellite imagery. So so whatever you want to add in, whatever you want to edit, whatever you want, all the data you want to feed in, you use this way of communicating with it. So the coding language that this thing is using that I'm using is, it's called JavaScript. So when you write your code, it will look something like this. So up here you can see your code, okay? And then this is basically the process of my work, to give you the rough idea of how it works. And then, so yes, but the thing is, if you look into the closely into the satellite imaging system, you can see that there are a lot of white dots. Okay, those are actually clouds, and and this is actually a major problem in our area in Southeast Asia, because this region, it's a tropical region, and therefore it's very difficult for the satellite to actually reach directly into the place where it wants to measure because of the cloud coverage. So the cloud is basically preventing it from taking measurement on ground measurement. So so this is where our ground, we use our device, this device called the Spectral Radiometer, to take a ground measurement on what's happening on the ground. So think of the Spectral Radiometer as something that's an instrument just like the satellite, but then the only difference is that it is on taking measure on ground. Say you want to measure a coconut tree, so you can have this device, Spectral Radiometer, in contact with the plant or the coconut tree that you want to measure, for example. And because of that, there is no cloud coverage problem, there is no other problems, so no other things that is preventing it from taking the real value of it. So this device, when you take the ground measurement, what it does is you feed, so what we do next is you feed this data from the spectral radiometer, say you feed it back to the Google Earth Engine platform. Say can you see the red dot? Hope the red dot will appear. So if you take, for example, ground measurement in this particular area with the red circle, and then after that you take that measurement and you feed in, means you add in the spectral radiometer data back to the satellite data that you have. Means you are doing data correction. For example, if your satellite is giving you the value of 1, but when you go to the same area and your satellite gives you the value of 2, you will tell the satellite that, hey, it's not 1, it's 2. 2 is the real value. So you do data correction. So once you're done with all that process, feeding in the data and everything, your model should look like this. So if you can see the model here, this is the very first model that I built. So this model, you can see that the green color ones are palm trees. I should be able to distinguish between palm trees, and the yellow area is actually other types of vegetation, not all palm tree. Yeah, and then but then the problem is it looks like a functional model. But the thing is, the problem with this model is that it has low resolution. So what do I mean by low resolution? So low resolution is like it's like this. So basically, if you take measurement on say your coconut tree, right, and you want to be able to feed in back that data into that coconut tree that you had measured earlier on today. But if you have very poor resolution image, you can't even identify where your coconut tree is. So that is where we need high resolution image, like the one on your right. So on your right, you can see that the image is better compared to the one on the left. And why is it better? So if you want to be able to detect where is the tree, say on the one that you have measured earlier on, you want to be able to see, oh, that's the tree that I had measured earlier on, and that's how it becomes useful. But when it comes to freely available satellite images, it's like very rare that you get a very high quality, high resolution image. So that is where the European Space Agency comes in. They are funding our high resolution data acquisition. So that's how the grant came about from them. And so now, like I said, I'm measuring plant health, building a models on plant health, biomass, and also yield estimation. So now let's look into what it does. You know, how, what can we know about it, and what should we do after knowing that okay, in the state of Sarawak, there are healthy plants, there are less healthy plants. And once you know there is this biomass and there is this yield estimation on all the plants, on the agriculture products in the state of Sarawak. So you want to be able to know what is causing it to behave in a certain way, which means what is causing it to be less healthy, what is causing it to be more healthier than the other plants. So that is where we are going to do biogeochemical research by analyzing the what's in the soil, what's in the parts of the plant, that this will help us to understand things that are happening in the plant, how understand why the plants are behaving that way. So the first instruments that I'm going to be using, it's called the ICP-MS, or inductively coupled plasma mass spectrometry. Don't worry about the jargons. So this basically what it does in this machine is it helps us to analyze the rare earth elements. So literally it's rare. This earth elements, they exist in such a small amount, but it has great impact on the health of the plant. And so because it has this great impact on the plant, we want to understand how does it impact the plant, how does it affect the plant behavior, how does it cause the plant to behave in a certain way. So that is it. And the next one, the next machine that we're going to be using is called the isotopic analysis. So this is basically to understand how the different nutrients in the soil affect the plants and how it behaves in the same way. So and the next thing is the synchrotron research. So the synchrotron research is basically, it helps us to understand things up to its atomic level. So I'm not going to get technical into it. So all of this future prospect, if everything works as planned, I'll be doing the second part of my master's in Australia next year. So I'll be heading to Australia in June to do the biogeochemical side of it. So, so I hope to be able to correlate or understand, to make the correlation between the biogeochemical process and also the models that I built by using the satellite data. So hopefully everything works and the way it should be. So yeah. I think this one, the first few months, I think I'll be spending it in Lismore, in Gold Coast, and I think the last 3 months will be in Melbourne. So this is the future prospect of my research. So yes, we are at the end of this already. So remote sensing, it's really, especially in this region, especially in Malaysia, actually, it's still very, very new. But then the ability for it to see the invisible and to reach the unreachable, it really tells us that, you can use this technology to do a lot of environmental monitoring work. And because it can go to the place that we can't go, or it can see it's really powerful. And because Malaysia is still very new and in this technology, I also think that when we collaborate, we can also benefit from all of it. So Malaysia is still new, but then Indonesia, especially in Kalimantan, Indonesia, a lot of researchers are utilizing remote sensing technology to understand the oil palm plantations in Kalimantan, Indonesia. And then in Thailand as well, it's very widely used. But like I said, Malaysia, it's still very new. So I welcome people who want to collaborate. I welcome comments and suggestions. So, you're free to reach me. If any of you who watch this live video or the recording later on, if you wanted to reach me, please do so. So I guess that's all from me, and yeah, that's my email address, so you can contact me if you wish to. Thank you. Yes, and also if there is any questions, you can ask me in the comment section. Mm. Yeah. I'm really really trying to figure out this. Thank you so much for being patient with me. And wait. Mm, yes. Okay, Albert, you have a question. Any challenges when your team did the data correction activity? Yeah. Okay, yes, that's a good question. Yes, actually, the main problem is the data acquisition, as in, say, for example, we need a very good um, high quality satellite image, because without the high quality image, you can't build a good model. So that is like the main challenges, and other than that, I think the ground ones are like just a little problem. I think when we want to do measurement in, say, a plantation site, not everybody will allow you to go and go to their plantation sites and say, oh, you can do measurement here. Sometimes there are actually a lot of times they're quite unhappy that you go to their sites and do measurements. But we are lucky that there are plantation owners who are very welcoming. So I guess not everything will work the way you want it to be, but yeah. It's fair enough, I guess. Yeah, I hope that answered your question. But if you're asking into like more technical terms on like the challenges in data correction activity, yes, because we are still figuring out the technology. We're still figuring out the technical side of it. I graduated with a bachelor's degree in biotechnology, but I'm currently doing something that is very, very different from what I studied in my undergrad. And since we also just got the ground, it's also like we're still figuring out how things work. But I hope it will fall to its places. Yeah, hope that answered your question. Mm, yeah, you can ask me more questions. I mean, it doesn't have to be related to the work. Actually, it can be like related to other things, my work and everything. Um, yeah. Mm, mm, well, also, I think that a lot of people, I would like to add on, I think a lot of people are actually, oh, yes, before that, Michelle asked a question. Yes, will the high resolution data be made available to public or only a selected organization? No. The high resolution data, it's not, if you're talking about high resolution data, the satellite image, high resolution data, no, it will not be made to public. That's why you need to request from, say, if you want to work with NASA, you have to request from NASA to get that. And sometimes in our case, our high resolution data, it's provided by a private company, it's a private satellite. So it's not available, it's not freely available, but they are freely available satellite data. However, However, it's not high quality, but it's good enough if you're just, starting your work in the research. And if you talk about, but if you are referring to after this, what will I do with the data? Will it be available? Well, I think it depends on the funding body, which is the main funding body is the Sarawak Multimedia Authority. Now, sometimes they don't want us to publish all of this data, but it's mainly for, because it's a government agency. So, we give this information to them and they will use this probably in a policy making process. But you, it's not, sometimes, most of the time, you can't publish it. It's not freely available. I think it's safe to say, either way, what you were asking, it's private and confidential, I'd say. And then your second question is, how will the outcome of this research help small scale farmers? I suppose that's what you meant. Um, well, this outcome of this research, it does not have a direct impact to a small farmer. It's designed, the research or the work it's carried out in such a way that it will help out the government for decision making process. However, there's a small part of my research, which is the one that I'm going to be carrying out in Australia next year. So that outcome of the research, hopefully I'll be able to help the small scale farmers who have this like who wants to decide whether or not to use organic fertilizer or inorganic fertilizer for their farm. I hope that the outcome of my research will be able to help them to decide between that, because one of the research questions that I have is what is the effect of using organic fertilizer versus inorganic fertilizer, or like the conventional fertilizer. So if we are able to understand this in by conducting all of these rare earth element RE analysis and the isotopic analysis, we might be able to understand it further. Um, yes, and how does it? Uh, can you share your past experience? Okay. Yes, thank you, Albert. Before that, thank you, Michelle, for your question. So yes, so I actually, how did my Wesley Academic Fellowship? I think this is a very reflective question, because I had not done it before. I never thought of it, but thank you for asking. So yeah, I actually started doing research, like summer internship with my professor, and doing like a lot of community work alongside that before I had joined YSILI. But these are like the small kind of research, small kind of work. But when I went to the YSILI Academic Fellowship, I met a lot of like-minded people who are very much into the topic, into the global environmental issues team. And then, I got a lot of insights from them. I got a lot of new knowledge, and I became more and more passionate about what I do. And at that point, when I was an undergrad, I wasn't so sure that environment is what I wanted to do. I was open to other opportunities, but then after coming back from the United States, I think, and from the YCD program, it really gave me the assurance that yes, this is what I want to do. Environmental research is what I am into. So that's why I decided to do my master's in that. Yeah, so that's how I relate. Nothing too technical though. I mean, if that's what you're asking, Albert, but nothing like no technical relation, but it's more to like helping me to like understand, to be sure this is what I want to do. Yeah, I hope that answer your question. Yes. Any other question? So yeah, you can ask me questions that are not related to my work at all, actually. Uh, yeah. Thank you. Mm, a question. Uh, um, yeah. Okay, so just give it. What else should I share? Uh, yeah. Anyway, I would like to say thanks to Albert for inviting me, and also Ria for inviting me to be a part of your program. I think this is really amazing work that you do. I'm really 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 impressed. Um, really really impressed on the thing that you do. It's really really amazing, and I hope that we can meet, Ria, and also with Albert next year as I go to Australia. Oh, thank you. Thank you. Yes, thank you, Albert. So yeah, but I guess I'm just gonna end this soon. But if you have any more questions, you wanna ask me, you can always drop me an email. You can liaise with Albert, or you can add me on Facebook. Yeah, Albert. Thank you so much for your wish. Yes, I hope we can meet again as well in Australia. Thank you so much.